In exercise 1C, we will have an example for the maximum margin classifier. And I gave you a table of observations where you should draw the scatter plot and the feature space. And then you should sketch the optimal hyperplane resulting from the fitting of the maximum margin classifier and provide the equation of the hyperplane. And I hope that you didn't misunderstand this exercise, or I think it could be very easily misinterpreted because you should not calculate the parameters by hand themselves, but we will talk now first before coming to these all the single exercises here from I to or from 1 to 4 about how to derive the weights for the maximum margin classifier, because this is an important process that you should have seen, and I think we've also covered that in the lecture, or at least partially. So how do we derive these weights? Well, we start with the Lagrangian. So this is the square of the second of the L2 norm. Oops. So I think you should be all familiar with this. This is just the Lagrangian of the maximization problem or the optimization problem that we had before. So we want to maximize the our margin, and which is basically covered here by the first part, and then we have this kind of subject or the conditions that that our optimization is subject to. So now let's first note down the first order conditions of the Lagrangian. So here we take the partial derivative of this function to a single weight, so weight j. So this is resulting, and now for optimality we need to set this equal to 0. And now if we do this for all our weights, so for all weights j from 1 to p, then we can save this in the vector, and write this down in back the notation. Then we do the same thing for our constant. I think I called it W0 before, but it doesn't matter, it's still the same. That's equal to 0 then, due to optimality. Then our I don't know what you call it, Lagrangian parameter alpha yields this partial derivative here. I think it's pretty intuitive. So now what we can do is we can plug them back into the Lagrangian to get a function that is no longer reliant on the weights. So this is again the L2 norm, or the square of the L2 norm. And here now I just pulled out beta out of the brackets, and then I multiplied alpha into the brackets, and this is the result. And now if you have a look at the first order conditions, then you will see that this part here is actually equal to 0, so this cancels out. Now let's pull out W. And now we can see, if we have a look again at the first order conditions, that this term here is actually also equal to W. So this is the sum of the alphas minus a half times this square of the alpha of the weight matrices. And now I can plug in the first order conditions for the W's. Or it's not the first order conditions, or it is, yeah, derivative to Wi. And then I get this equation here, I plug it in. And then we get this this form of the Lagrangian that you know from the lecture. So this is how we actually derive it. And now, why did we do this? Because now the only parameters we are left are alphas. So we can more or less pretty easily optimize this, as we have as much alphas as we have observation points. So we can get our estimates for alpha, and then we can get the support points or support vectors, because they are defined as if alpha is greater than 1, then this condition is true, and therefore this will be a support vector. So if this condition is, if alpha for an individual observation is greater than 1, then this observation is a support vector. And using those, we can calculate our estimates for the weights. And this seems complicated, but it's actually computationally relatively easy. And if we would have still all the our weights inside the Lagrangian, we had way too much parameters to optimize that. So that's why we have to do this procedure. Okay, and this is basically how we will calculate our weights in the end.